with these 1.2 notes, we left off with domain and range, but really we want to talk about a ton of key characteristics. Domain and range are only a couple. And so we're going to dive in those. We got a lot of vocab that we are going to run through, but I think it'll be okay, and I promise I'll give you lots of opportunities to practice it. Okay? So as we get started, the very first one is about continuity, right? And basically we're talking about whether a graph is continuous or discontinuous. And a graph is continuous if it can be traced. It can be fully traced without lifting. Lifting your finger, lifting your pencil, whatever you're tracing with. So we're going to look at 4 examples. Okay, the first graph, make it an absolute value graph. That graph's continuous. The reason that graph is continuous is it's smooth. If I put my pencil on that left arrow, follow it down, bounce off the bottom, and bounce back up, I can touch everywhere on the graph without ever worrying about having to pick up my pencil. Okay? Now we're going to get into our discontinuous graph. So the first discontinuous graph has what's called infinite discontinuity, and that happens when you have an asymptote. So in this graph, we've got kind of an asymptote here where the left side of the graph is going down to negative infinity, and the right side of the graph restarts at positive infinity. So this graph is discontinuous, and it has what's called infinite discontinuity. Because of the fact that the arrows are at the infinities. Okay? Another type of discontinuity is called a jump. In other words, our graph makes a jump from one spot to another. So this is discontinuous with a jump discontinuity. And our final type, at least for what we're concerned with, has just a hole in it. And you're like, Visto, I can draw that hole without lifting my pencil. The picture is different than the graph, right? And so we have to imagine that there's a chunk of graph missing at that spot. And so that's why this graph is discontinuous. We call this a removable. You may also see it called fillable because we could like plug a number in and it would be just fine. Not disability. Oh my gosh. Discontinuity. Let's try that again. Discontinuity. The reason it's fillable is because we could actually put a point right there and fill it in, and then our graph would be totally continuous. But this is when our graph has a hole, which is something you did talk about in 2E back in the day. So just something to be mindful of is you did do a little bit with holes in chapter 8 last year, so hopefully that language is familiar. We'll dive into it a little more in a little bit. Okay, the next thing we can talk about with the graph is where is that graph increasing and where is it decreasing? When we talk increasing and decreasing, we always read the graph from left to right, and we focus on the x values of specific spots in the graph. So I'm going to draw a graph, make it nice and long. Here's what I'm going to do. I'm going to have it coming down here. And then there's going to be a first x value at A. And at A, the graph's going to be constant to B. Then my graph's going to drop way down here to at a point for C. Pop back up for D. And then just for fun, we're going to have it drop again. Okay? So if I read my graph left to right, if I take and put a person on the left side of the graph and ask them to walk to the right side of the graph, following the graph, right? So if I put a cute little person right here and ask them to follow the graph, right now they would be climbing uphill. Our graph from 0 to A is increasing. From A to B, that's constant. Now, something as I'm writing these are not ordered pairs. I'm using interval notation. So if you need a little review on interval notation, I'd love to help you with that. Please reach out and let me know. But basically, I'm talking about the interval from 0 to A and the interval from A to B, right? Because A and B are both x values, so we wouldn't have two x values in an ordered pair. Then from B to C, we are decreasing. From C to D, we are increasing. And from D, and since we're talking about the x values, from D to infinity, we are decreasing. And it feels weird to say infinity, but you got to remember, we're reading the graph left to right, and we're following all the way over to infinity on the graph. The graph's never going to turn and come back up. As far as we go to the right to infinity, we're always decreasing. So that's kind of our information about increasing and decreasing. It's all about just reading the graph and picturing what our little person would be doing. I'm going to move that just so I have a little more space to write. Hopefully your notes are working out okay. Next thing we're going to talk about, is our extrema. Okay? New word, but I think you'll do all right. When I see extrema, I see the word extreme, and then I see the in the back. Just like data or data is plural, extrema is plural. And it means more than one extreme. You might hear pronounced extrema. I like to say extrema. Makes me remember the other word that's in there, which is extreme. Big long graph again. I am going to mark my y-axis in this case. So I've got a 0, 1, 2. Because I think that'll be helpful. The x-axis I could care less about. We're just going to use letters again. So here we go. My graph's going up. Got a point right there. Then my graph is coming down. It's got a point right here. And then it's going way up high. I'm even up above the word extrema. And then I'm coming down again. The x values for each of those spots are very creatively named A, B, and C. So let's talk about this graph. First of all, this graph on the left side is going down to negative infinity, and on the right side is going down to negative infinity. However, on the up parts of this graph, we've got some maximums, including a global or absolute maximum. Let's talk about point A first. We have an ordered pair at A2. At this ordered pair, our graph switches from going increasing to decreasing, and so we have what's called a local maximum. A local maximum happens because of this increasing to decrease, and it's like a tiny little hill on our graph, right? A local maximum would be maybe the highest point in Mankato. On the other hand, at C, we're all the way up to 4, and this is the highest point on the entire graph. The graph never gets higher than 4, so we call this a global or absolute maximum. This would be the Mount Everest of our graph. Our graph never gets higher than this point. Okay? As far as minimums go, when we go all the way down, turn and come back up, this graph has a local minimum at B -1. It does not have a global minimum because of the fact that those arrows are going down forever. So those are our extrema, local maxes, absolute maximum, local minimum, absolute minimum, or global. Those words kind of are interchangeable. The next thing we can look at for our graph is our graph bounded? In other words, can our graph fit totally above a line or totally below a line? So let's draw 3 graphs. 1, 2, 3. First graph I'm going to make kind of like the graph we just did, almost like the letter M. And I am going to put a horizontal line. I'm going to attempt to put a horizontal line fully above the graph. Because it is above the graph, this graph is what's called bounded above. I can draw a line above the graph. The next graph, I'm going to put a horizontal line completely below the graph. This graph is bounded by a line below it, so we say bounded below. The third graph, kind of give it this wave action. This graph, I can put a line completely above it, and I can put a line completely below it. And I'm going to say that this graph, because I can do above and below, I'm just going to say it's bounded. You may hear it said bounded on its domain. But the idea of being bounded means it's bounded above and it's bounded below. Okay? Another thing we can say about graphs, we're just going to keep talking about graphs and equations, and you're going to do great. I know you will. The next thing we can talk about is symmetry, the symmetry of our graph. There's 3 ways our graphs can be symmetrical. So I'm going to draw 3 graphs. 1, 2, 3. First of all, let's draw this graph. This is the graph of x equals y squared. Okay? So this graph has symmetry across the x-axis. Fun fact about this graph, it's not actually a function because it fails the vertical line test with this symmetry. Okay? Great. Kind of boring. We're not going to look at too many like that this year. Here's the next one we're going to look at. I'm going to draw an absolute value equation. This absolute value equation has a line of symmetry across the y-axis. This type of symmetry is called even. This graph is even. In terms of notation, the function evaluated for negative x is the same as the function evaluated for positive x. In other words, if I talk about 3 and negative 3, they both have the same y value. The third type, if we have even, we should probably talk about odd. And odd symmetry looks like this. It's symmetric across the origin, but what I like to think about is that it flips horizontally and it flips vertically. But the official definition, it is symmetric across the origin, which makes it odd. As far as looking at it in terms of function notation, if I look at a negative value of x, that's equal to the negative f of x. So let's look at this. So I'm just going to use this 1 right here. 1 has a point at 1. If I go over to negative 1, the y value is the opposite. Okay? And maybe 1's not the best point. Maybe I'll look at half has a value of, it's a cubic, so I'm going to say that's 1/8. And if I go to negative 1/2, it's at negative 1/8. Okay, that got a little bit clustered, but we're looking at the fact that we flip across and down. And a pattern we can notice with some of the symmetry stuff is, what is the exponent? Is the exponent even? Chances are your graph is even then. We're doing great. Got a couple more things to talk about, and then we'll be done. The next thing is end behavior. In other words, what are the ends of the graphs doing? What are the arrows on your graphs doing? We're going to look at 3 graphs. Hopefully you're getting really good at drawing axes. Mine have not gotten better as we've gone on, but that's okay. We're going to do our best. So in these three graphs, in this last one, I'm going to mark off my axes. Okay. In these three graphs, I'm going to focus on one spot in each graph. In this graph, I'm going to focus this right-hand arrow. And here's what I'm going to say. Since I'm looking at the right side of the graph, I'm going to say the limit as x approaches infinity. In other words, as I go off to the right side of my graph, this function is going up. So as I go right, my graph is going up. So this is the part that talks about the right, that's the part that talks about up. Okay. In the next graph, I'm going to look at the left-hand arrow. The left-hand arrow, as x approaches negative infinity, that's the left side of my graph, this particular graph, f of x, and there's positive infinity because the left side of the graph is going up. This third graph, if I look at the right side of the graph, the limit as our graph goes off to the right of this particular function, f of x. Remember, f of x is just the name of a function. As this graph goes off to infinity, it is approaching an asymptote, and it is approaching 4. We know it's 4 because we labeled our axis. So that's another thing that can happen. You can approach a number. A lot of times we like to approach 0. Okay. Speaking of asymptotes, we just got a little bit left. Asymptotes, remember, asymptotes are lines that our graphs approach. We can cross asymptotes, but never at the infinities. Sometimes we'll cross them kind of in the middle of our graph, but never out at the edges. So here I'm going to go draw a graph. And I'm going to make my graph do something like this. Ooh, maybe not quite like that. Let me try that again. I didn't get my graph to start in a good spot because I want 2 asymptotes on this graph. I want a vertical asymptote and I want a horizontal asymptote. Okay? Couple quick reminders about some things with asymptotes. Horizontal lines, whenever we're talking about a horizontal line, it has a slope of 0 and the equation is y equals. Vertical lines have an undefined slope and their equation is x equals. So we can think hoi, vux to help kind of guide our thinking on some of these asymptote things. Okay, back in action. Asymptotes. Horizontal asymptotes occur at equations y equals b, right? We said horizontal lines y equals if the limit as x goes to either infinity approaches b, or as we go off on the left side of the graph to negative infinity, our graph flattens out at b. So the big thing is horizontal asymptotes are lines where y equals b. Vertical asymptotes occur at x equals a if x approaches a from the left and the graph is going either up or down, or x approaches a from the right and the graph goes up or down. Wholly intense definition. My favorite way to find asymptotes is to look at the graph, right? So if you're looking at your graph, you should be able to see asymptotes based on what the graph is doing. Really quickly though, let's do a quick example. F of x, oops, let's make that a little bit bigger. Our function f of x in this case is 5 over x plus 3 minus 6. First of all, we'll start with the easy one, your vertical asymptote. Vertical asymptotes occur anytime you have something in the denominator that causes it to be 0. So we've got an x plus 3 in our denominator of this fraction. What will make that 0 is negative 3. So we have a vertical asymptote at x equals negative 3. Our horizontal asymptote, I'm going to give you the technical definition and then I'm going to say, graph it! Let's look at what happens when we bring x to infinity of this equation. This part right here, as x goes to infinity, as x gets really, really big, that's just going to equal 0. Reason being is because if x is huge, dividing by a big number makes a very, very small number. If I had 5 cookies to share with 5 people, each person gets a cookie. If I had 5 cookies to share with 50 people, each person gets maybe a small nibble. If I had 5 cookies to share with 500 people, each person gets to lick it. If I had 5 cookies to share with 1 billion people, each person gets an atom of the cookie, right? That piece gets smaller and smaller to eventually where if I had 5 cookies to share with 500 billion people, no one's getting anything. I'll just keep the cookies for myself. So that's why that's going to 0, which means, oops, my bad, this graph has a horizontal asymptote at y equals negative 6. Right, because the negative 6 trailed down as we went through that. I realized I got talking about cookies. Final thing, holes. We talked about them once already. I'm going to give you a quick little review. Holes are removable discontinuities. They occur when the numerator of a fraction and the denominator of a fraction have the same factor. Quick example. I might have something that has x plus 3 and x minus 3 in the numerator. And the bottom might also have an x plus 3. Because they both have an x plus 3, we have a hole when x is negative 3. There's the part that's the same. I set that equal to 0, and that's where I get my negative 3. Okay? Tons and tons of notes here. I'm going to stop. As you're processing